Okay, now we'll talk about heat transfer. And you know that heat flows from a hotter object to a colder object. So here, this picture illustrates 3 different modes of heat transfer: conduction, convection, and radiation. So for instance, if you want to get some heat from here to this person, you can stick a metal rod in there and heat is transferred via conduction through the rod to you. This is electromagnetic radiation transferring heat to you. So that's radiative transfer. And you can hold your hand up there and you feel the warmth. And most of that is convective heat transfer. You're getting radiative heat transfer as well. What's happening is the air around the fire is warming, is being warmed. Warm air expands, it gets less dense, and it rises. And that warm air is transferring heat to you. Okay? So that's convective heat transfer. And that's why a candle flame is pointed up like that. Okay. So the candle flame warms the air and the air rises. And so these light are from excited atoms and ionized atoms that you see. So you see this flame rise like this. So for instance, if you lit buoyancy can only occur in a gravitational field. That is, warm air can rise only in a gravitational field. If you lit a fire out in space, in a 0 gravitational field, warm air wouldn't rise. And so that's what's shown here. So here's a candle burning in the space shuttle, and the flame is spherical. Okay. So anyway, so what we are interested in is heat transfer via these 3 modes: conduction, convection, and radiation. So first we'll look at conduction. So conduction, we're mostly interested in conduction in solids, even though liquids and gases transfer via conduction as well. But in gases, conduction is a small portion. All right, so here's how conduction happens at a molecular level. So in a solid, atoms are in a fixed location. So when this side of the solid is hotter, these molecules are vibrating with large amplitudes. Their average kinetic energy is higher than the colder side. And heat transfer via conduction happens. These guys bump into their neighbors, share some of their energy, give that some of their energy. These guys then bump into them and so on. So eventually energy gets transferred like that. And if this was an isolated system, eventually this will come, the whole system will come to a uniform temperature. All molecules on the average will have the same kinetic energy and no more heat transfer will occur. Okay? But if you maintain a temperature difference, heat will flow from the hotter end to the colder end. Heat will flow from the hotter end to the colder end. And the rate at which heat flows depends on the property of the material, the thermal conductivity of the material, times the area of cross-section, times the temperature gradient. This is the temperature difference divided by the difference in distance. That's the temperature gradient. Okay? The rate of change of temperature with distance. And heat flows in a direction of decreasing temperature. So this would be negative, and that's why the negative sign. Okay? So the rate of heat transfer is thermal conductivity times the area of cross-section times the temperature gradient. And of course, so during the winters and stuff like that, when you're heating the inside of your house, you don't want the heat flowing outside. So you want to make the walls with small thermal conductivities. Okay? So you fill it with insulation and so on. So as engineers, you have to worry about this number. Okay. All right, here's another problem. We live in the digital age and we can't live without computers. Okay. And a computer, a laptop or a desktop is roughly a 100-watt device. But there's all the electrical energy being used is converted to heat. Okay, so, and these darn chips do not work if they get too hot. So you have to continuously get rid of that much heat, 100 joules per second from a single laptop. from a single CPU. Now, server farms can have as much as 10,000, even more CPUs running in a small room. And they have a power consumption of 1 megawatt. So in one room, you have 10,000 computers sitting and consuming 1 megawatt, which is the same power consumption of 1,000 homes in one little room. So server farms, energy management is an issue. You better have good air conditioning. Okay. So imagine your air conditioner breaks down, all those CPUs would heat up, and all those machines are running some banking system. You cannot shut them off. You have a problem on your hands. So anyway, so you have to worry about all those problems. So in this device, so the CPU is in touch with this piece of metal, and it's losing heat via these fins, and there's this fan blows air through the fins. That's how each system is being cooled. Anyway, so here's heat transfer via convection. Here's how heat transfer via convection happens. So here's a heater, a space heater. This warms up air around it. The air gets less dense, rises, and it gets replaced by cool air. And eventually all the whole room can get warmed up. Okay. So that's convective heat transfer. So in convective heat transfer, the liquid or gas molecules are actually being transported. In conductive heat transfer, the molecules stay in place and they just transfer energy via bumping into neighbors. Okay. So in convective heat transfer, the material substance itself, warm substance moves around and transfer heats. Okay. So the Gulf Stream transfers enormous amounts of heat from the Gulf of Mexico northward. So here is the Gulf Stream. So here are the tropical latitudes, which get a lot more heat. The water is much warmer, and that warm water travels up north. Okay. So here is a bigger picture. So here's all warm water, and it goes through the Straits of Florida, and here's a stream of warm water. And this stream of warm water, so the Gulf Stream is typically about 100 kilometers wide. So here it's about 100 kilometers wide and a kilometer deep. And this stream of warm water is flowing at about 5 to 6 miles an hour. And the way this was discovered was in 1500, Ponce de Leon discovered a current against which he could not proceed. Okay, so he was sailing in this direction, and even though he had favorable winds, he was not going anywhere. And he realized the water was flowing in that direction. Okay. So that's how this was discovered. The Gulf Stream was discovered. Okay, here are some amazing numbers. So the Gulf Stream transports 30 million cubic meters per second through the Florida Strait. So this water is about 30 million cubic meters per second. And here it's about 105 times greater. So 150 million cubic meters per second. And this stream of water, warm water, the volume of Gulf Stream dwarfs all rivers that empty into the Atlantic Ocean. So what is all emptying into the Atlantic Ocean? The Mississippi, the Amazon, and so on. Those are the two big rivers. And those two rivers only empty about 1 million cubic meters per second. So this river is 150 times more, transports 150 times more water than the Mississippi and the Amazon. And still, the Gulf Stream is weaker than the Antarctic circumpolar current. There's a warm current flowing around Antarctica. Okay? And this thing is weaker than that. Anyway, The point is nature transfers enormous amounts of energy compared to human scales. Okay, now we'll look at radiative heat transfer. All objects emit electromagnetic radiation. So, and this temperature is an absolute scale. So the power radiated depends on the emissivity. This is a constant between 0 and 1. Okay. So an ideal emitter has E equal to 1. Sigma is the Stefan-Boltzmann's constant. That's the same for all objects, which is that. A is the surface area of the object, and T is the temperature in Kelvin's absolute scale. Okay. So if you're not at absolute 0, you're emitting electromagnetic radiation. Okay. Only when you're at absolute 0, then you want to emit electromagnetic radiation. And as you know, nothing can get to absolute 0. So all objects emit electromagnetic radiation. So let's say you're in a room, your body temperature is T and the surrounding temperature is T naught. The net radiative loss is that, okay? Because that object was emitting radiation and you were absorbing some. Okay? So the net loss is E times sigma times A times T to the power 4 minus T naught to the power 4. Okay, so this diagram illustrates this. So here's a picture taken using visible light, and here's a picture taken using infrared light. Okay, and the infrared light is able to get through this garbage bag. So the emissivity is 1 for an ideal absorber, also known as a black body. And an ideal reflector is where the emissivity is 0. So any radiation falling on the object is reflected. Okay, so by the way, the stealth aircraft, so for instance, the stealth is radar and all bouncing off of this. So it's scattered and absorbed. So it's an ideal absorber, sort of. Okay. And black objects are good absorbers and white fabrics are better reflectors. So in the winter, you want to wear black fabric, and in the summer, you want to wear white fabric. Okay. So here's a good absorber. It reflects very little radiation. And if you're a good absorber, you radiate, you are a good radiator as well. So if you're a good absorber, you're a good radiator. If your temperature is high, you emit a lot of radiation. If you're a light object, then you're a good reflector. And by the same token, you're not a good radiator as well. And that's what this is showing you. All right, I'll pause for a second and quickly go over the greenhouse effect.